Good morning, everyone. First of all, I would like to thank the organizer for giving me the opportunity to be here today and to share our results with you. I came from Poland, from Silesian University of Technology. I'm working in the Department of Chemical Organic Technology and Petrochemistry. Today, I will tell you about how we design in my group catalysts, which are recoverable and recyclable, and which can be used for the sustainable chemical processes. So what are the challenges for the sustainable chemical industry today? First of all, as we know, is to reduce chemical waste and to improve the selectivity and efficiency of synthetic processes. And it can be done by designing of and synthesis of recoverable and recyclable catalysts. And that's what we do in our department. The need to improvement green chemistry principles is a driving force towards the development of recoverable and recyclable catalysts. And how can the recyclable can be achieved? First of all, by bonding the catalyst to the solid surface, and also by the modification of the solubility characteristics. And those examples I would like to show you today. So, for example, when we have the catalyst, acidic or basic catalyst, we can bond it to the solid surface, and then after the simple filtration, we can isolate them, make the regeneration, and then recycle. So as Professor Martin Lungo already said, the green chemistry is very important, and let me remind you, this is the design, development, and implementation of chemical products and processes to reduce or eliminate the use and generation of substances which are hazardous to human health and the environment. And the catalysis is one of the green chemistry principles, and by the definition we can say if we have the catalytic system, it is green. But in fact we have some green chemistry factors like environmental factor, which can tell us how much of waste we produced for 1 kilogram of product. As you can see from the scheme, from this table, we have a big problem in the farm chemicals and pharmaceuticals sectors, and there is a lot of byproducts. And my group is working on the development of new catalysts for the fine chemicals and pharmaceuticals production. Today I will show you a few examples concerning the designing of catalysts for the processes like esterification, Diels-Alder reaction, and also the oxidation of alcohols and ketones. To this aim, we use ionic liquids as a homogeneous or heterogeneous catalyst. And why the recycle of ionic liquids is so important? Because we prevent, by recycling of those salts, we prevent them from ending up in the aquatic environment, and also we don't have to take care a lot about the release into the atmosphere because they are of the low volatility. In the end, I will show you also how we can design ionic liquids from biomass. Just a few words about ionic liquids. Those are salts which possess organic cation and also inorganic or organic anion. And those salts are mainly tetraalkyl ammonium, tetraalkyl phosphonium, dialkyl indosolium, or alkyl pyrimidinium salts. What is very interesting in ionic liquids? They are excellent solvent for both organic and inorganic solutes, and this power to dissolve so many substances makes them also very efficient catalysts. I will show you an example in a minute. They are also no volatile, as I already mentioned, and no inflammable, and they have an excellent oxidation reduction stability, excellent thermal stability, what is very important in the recycling. And what is the most important, they are liquids in a very broad range of temperatures. As you can see from this slide, we have one butyl free metal imidazolium tetrafluoroborate, which is in the oil bath, like 171 Celsius degrees. And you can see on the pressure, it is still a nice liquid. The first example will concern the use of ionic liquids as catalyst and solvent, both, for the esterification reaction. And on this example, I will show you how we can modify the solubility characteristic to make the system recyclable. For the esterification reaction, we need acetic catalyst, and to this aim, we propose to use ionic liquids which are based on the complex hydrogen-bonded ionic clusters. So we can easily prepare them, thinking in terms from the cradle to the grave, that we can use just sulfuric acid and base, and we use as bases like metal imidazolium, 3-alkyl amine, and also metal pyridine and others. And we can use the different proportions or acid and base, and we can obtain a nice liquid at room temperatures. First of all, we had to, of course, determine the structure, and we find that they create a complex hydrogen-bonded ionic clusters. So we can see that in the hydrogen sulfate anions, we can find the clusters. Depends on how many sulfuric acid we use for the synthesis of ionic liquid. And those acidic ionic liquids we use for the esterification reaction. We choose as a model reaction just a simple acid like acetic acid and also butyl alcohol. And first of all, we perform the optimization. We determine the catalyst acidity, and we also determine how much of catalyst we need for the system. And we establish the reactant ratio, and what is very important and what we do always when we perform a new method for the synthesis. We also check the possibility of a catalyst recycle. As you can see, we need only, let's say, around 10%, mole percent of catalyst to perform the esterification reaction at 30 Celsius degrees very efficiently, even up to 90% yield of ester. When we use the excess of acid, we can even obtain almost 100% yield of ester at room temperature. So, how it happened? It is caused by the changing of the solubility of substrate and products in ionic liquid. So, in the beginning, we have homogeneous system when the alcohol and acid is dissolved in ionic liquid. And during the reaction, the second phase is formed. This is the ester phase, which is undissolved in ionic liquid. And also it is very important in the pushing the equilibrium toward the product formation, because this is the equilibrium reaction and this is how we obtain such a high yields. And using these ionic liquids, we could easily isolate the product just by decantation, and then we can easily, with high efficiency, recycle it several times. So that was the first example concerning the solubility. And the second example is will be about the designing of recyclable biocatalyst. So we know that it would be nice to avoid using metal catalyst. And this is just the example how we can eliminate metal catalyst from the Diels-Alder reaction by using ionic liquids, which are as effective as metal catalysts. This is the example how we design the cation of ionic liquids using the glucose, just the changing the structure in the on the one carbon on the one carbon of glucose, and we can obtain tetraalkyl ammonium salts, which are still liquids, very viscous, but still liquids at room temperature. And we apply those ionic liquids as organocatalysts, so in catalytic amounts for this system to, and we could obtain high yields of products and also high stereoselectivity. So that was another example how we can eliminate metal catalysts, how we can avoid product formation. And this is the example of other reactions, Diels-Alder reactions. In all cases, we obtain high yields and high selectivities. Another examples will show you how we can bound the catalyst to the solid phase, and how we can recycle it and use it in ketones oxidation. To this aim, we use as a catalyst carrier, we use bimodal structured silica, and we bounding the ionic liquid via the cation to the surface of silica. As you can see, as a counter anion, we use hydrogen sulfate anion, which makes this catalyst acidic. So we can obtain a nice solid catalyst, which could be easily removed from the reaction system. As I said, we use this acidic catalyst for the oxidation of ketones in a very simple reaction system. We used hydrogen peroxide as an oxidant, and just after the reaction, we can easily filtrate the catalyst from the reaction system, and then we can recycle it several times. And what is more important, with the very high catalyst recovery, this data is very often missed in the literature, but it is still important, not only that we can recycle the catalyst with high activity, but also with high percent of catalyst recovery. And the last example, which I present you today, is the use of ionic liquids as catalyst and solvents for the alcohol oxidation. We call this technique supported ionic liquid phase. So we can design the catalyst just by using solid support as silica. We can introduce on the support the active site, our real catalyst, and we can cover this solid phase with the thin layer of ionic liquid. So it is not bonded with chemical bond to the surface, but this is just a cover. Yes, so it is covered by ionic liquids and interact with the solid surface by the van der Waals interactions. So in fact, we can design the solid catalyst, but from the opposite side of view, we can also use it as a homogeneous catalyst, because the reaction takes place in a thin film of ionic liquid. So the reagents are dissolved in ionic liquids, they get into the contact with the catalyst, and then the product can be easily can enter to the another phase. It can be a liquid phase or gas phase. And after the reaction, we can isolate this catalyst, which is in fact solid catalyst. So we can also use the proper amount of ionic liquid to obtain the solid catalyst. We design two kinds of supported ionic liquid phase catalyst. One of them is just a bimodal post-structure silica, which is covered with octyl sulfate ionic liquid. And in this ionic liquid, copper chloride is dissolved, which is the real catalyst for the oxidation reaction. And also, we can use different solid support, ionogel, which is already prepared from the ionic liquid, and silica gel. And also, we can use copper chloride already on the stage of the formation of the solid phase. So then when we cover the solid phase with ionic liquids, the interreactions are a little bit stronger. And still those are solid catalysts. As you can see, we use them for the alcohol oxidation. We observe high conversions, high yield of aldehydes during relatively low time. And what I also show here, we obtain high catalyst recovery, like 90 to 93%. Of course, if we can perform this reaction in the bigger scale, then the recovery of the catalyst will be for sure higher. And this is just the scheme for the reusability of those both catalysts. As you can see, they are very active in 7 cycles of the reactions, both of them, and we can observe on small drop of the activity in the 7th cycle. And to summary, the development of the recyclable catalyst represents a big challenge. It is an interdisciplinary field when the pure chemistry is connected to the material science, engineering, and where even business and economy-related issues play an important role in determining the planning, the design, and the realization of the project in this area. It is a field where many technologies and opportunities are offered to successfully realize and easy recoverable, and what is more important, reusable catalytic systems. And I hope I presented you on those couple examples how we do it in our group. I would like to thank my PhD students and also the group of Professor Jarzemski from Poland, which designed the solid support for us, and also Professor Kenneth Seddon from Belfast University. We cooperate together in a research field of ionic liquids. And also I would like to thank National Science Center in Poland for financing our works. And in the end, I would like to thank you for your attention.
Thank you, Ms. Chrobok. We have time for questions. Okay.
Thank you. I would like to ask the surface area of the silica you used, more or less 100, 200 meters, 300 meters per gram.
Yes, 1 to 2 per gram of the ratio of silica to ionic liquid, mass ratio.
And is it commercial or is usually was to death?
Yeah, we use commercial, but also we use the bimodal pore structure with the very developed system of micro and mesopores. Oh yeah. It was No, it was crushed, so it was just like a slurry system.
It's because we are preparing at the moment in the project, we are preparing silica from rice husk, and we would like to speak with you later on because we have silicas of several surface areas, and maybe you may be interested in putting together ionic liquid, which I think is an enormously interesting subject, obviously with this kind of silicas, please.
Okay, thank you very much. It would be very interesting.